Hello everyone. So this is the second lecture of thermodynamics, and in this lecture we'll discuss about ideal gas equation in different types of thermodynamics process. Okay. Now I'll not transit from what you say English to Hindi. I'll now continue in English. I said due to some reason, so I cannot continue in Hindi. So ideal gas equation in different types of thermodynamic process. Okay. Don't ask for reasons in comment. Okay. I can't say. Okay. Let me start now. Ideal gas equation. This time slides are taken black so that things are pretty visible. Ideal gas equation. So this is PV is equals to nRT, where P is pressure, V is volume, N is number of moles, R is universal gas constant, T is temperature in kelvins. R is called as universal gas constant. Its value is 8.314 SI units. Okay. This is something. P is pressure, V is volume, N is number of moles, R is universal gas constant whose value is 8.314 in SI units. T is temperature in Kelvin. Now this was ideal gas equation. Now talking about different types of thermodynamic process. So there are 4 types of thermodynamic process generally which we have to study. First one is called isobaric. Second one is isochoric. Third one is isothermal. Fourth one is adiabatic. Okay, so these are the 4 types of thermodynamic process which we say thermodynamic process which we have to study. There is one more, that is polytropic process, but that is not in our main concern. Okay, these 4 are our main concern. Okay, that is polytropic. It means you can say advanced form of adiabatic process is polytropic process, but that is not in our discussion right now. We will discuss mainly the 4 types of thermodynamics process. Let's start. Firstly, isobaric process. Isobaric process is the process in which pressure is constant, and when pressure is constant you can see PV is equals to nRT, R is constant, universal gas constant. We have taken also number of moles constant. This is also taken constant. Both are taken constant. Pressure is as per the definition constant. So here volume is directly proportional to temperature. So for isobaric process we write V1 by V2. We can write V1 by V2 equal to T1 by T2. Okay. Now talking about graphs. So if you will plot, next slide I'll show you the graphs. Okay, so if you'll plot pressure versus any other parameter, then pressure, other parameter other than pressure, it will come as this, because pressure is constant with respect to any other function, any other coordinate, whether it is time and number of moles, whatever. But talking about in this process we are discussing, if it is given as volume is and temperature, then then it will go as a, what you say, y is equals to mx type graph will be there, where m is the slope which will be given by the tangent of this angle theta, it is tan theta. Okay, this is your uh, isobaric process. Now let us discuss about isochoric process. Isochoric process, so it is process in which iso means same, the process in which volume remains constant. Now, considering the ideal gas equation, this is constant. These two are also constant parameter. So pressure is directly proportional to temperature. And see, when I'm writing volume is constant, the derivative will be zero. This we will discuss. This concept we will discuss when I will find work done in different process in next lecture. Okay, so this we will discuss. Okay, differentiation of a constant is zero. That we will use when we will find work done in different process. Here pressure is directly proportional to temperature, so we can write P1 by P2 is equals to T1 by T2, and this is the thing, isochoric process. And let us plot this graph also. If we plot volume versus any other reaction coordinate, or other coordinate system with respect to other coordinate system, it will come as a straight line parallel to the x-axis. Okay, when naming it y-axis, we are naming it x-axis. Will come parallel to the x-axis. Okay, now talking about the next thing, that is your pressure versus temperature. It will come as a curve of y is equals to mx, where same this theta dash you can say m is equals to tan theta dash, or you can write m dash also, whatever be the slope of that particular line, that will be given by the tangent of that theta, as you know already. So this was isochoric process. Now let us discuss about isothermal process. Isothermal process. Therm means temperature. Okay, therm is generally refers to temperature. So here temperature remains constant. Okay. So since temperature is constant, we can write. You can see from Nust. What do you say? Ideal gas equation. Sorry, I said Nust equation. These three parameters are constant. So product of pressure and volume is seen as constant. So P1 V1 can be written as this, where pressure is inversely proportional to volume. As we can see from this, we can say that PV, product of pressure and volume, is constant. P1 V1 equal to P2 V2. Okay. Now if we plot like this, see here no any coordinate. Here we'll write any coordinate, and here we'll take temperatures. It will come as this, because temperature is constant. Whatever be the temperature, there is a particular temperature, and the reaction will proceed at that particular temperature in the whole its journey. So that temperature remains constant. Talking about pressure volume curve, so it will come as this. We can say a hyperbolic curve. Y is inversely proportional to x. This is a hyperbolic curve, so it will come as this. Okay, but if you will plot the graph of PV and temperature, it will come like this, straight line parallel to temperature axis. Clear? So this was our uh, isothermal process, and I think you understood. Now we will move to adiabatic process. Fourth one and the last one, adiabatic process. It is a very special process because in this process heat exchange is zero, means no exchange of heat between system and surrounding. So there are some, you can say, like we discussed, PV is equals to constant for the uh, isothermal process. So we will relate these processes in finding the work done also in writing the first law of thermodynamics, which we will study in next lecture. Next lecture we'll discuss the first law of thermodynamics, and then we will relate it with the different thermodynamic process which we have studied, which we studied today. Okay, so Q is equals to 0, and we can write there are three particularly cases here, which we write PV raised to the power gamma is equals to constant, T V gamma minus 1 is equals to constant. Just using the you can say again ideal gas equation. So you write P as nRT by V, and you will get this. I'm making you drive this. Next slide. Okay, next slide. Let me write first of all results. So pressure like this. What is gamma? Everything we will discuss. See, gamma is first of all Cp by Cv. What is Cp? What is Cv? Let us discuss a little bit. Okay, because these are the part which we'll discuss in the next lectures. This is called adiabatic constant. Cp is molar specific heat, SH specific heat at the rate constant pressure, and this is the same at the rate constant volume. Okay, so this is the thing. Now talking about CV, there are several manipulations of CV. Our next lecture will be a lengthy lecture, because in that lecture we will discuss a most, you can say, the core of thermodynamics, that is first law of thermodynamics, and its different you can say formulations, and the discussion of CP, CV, everything will be there in the next lecture. I decided to take one lecture, a little lengthy. It will stretch to 40-45 minutes. Next lecture. This lecture will be around 15 minutes. Around 15 minutes. So adiabatic constant, gamma is adiabatic constant, Cp over Cv. How we can transform it, that I can discuss now. Pv power gamma is equals to constant. From this we can write nRT over V into V gamma like this. Now nr is constant, we can send it to the RHS side, and that again will be a constant. So TV gamma minus 1 is equals to constant. Again writing volume in terms of temperature and pressure, it will be like this: nRT by P power gamma is equals to constant. P is equals to 1 minus gamma T power gamma is equals to constant. And here we go with the three results which we have just stated in the previous slide. Okay, so this was our thermodynamic process. Next lecture will be, again I say, it will be lengthy lecture, 40-45 minutes, even if we reach to 50 minutes also, because many concepts we have to discuss. I'll discuss with you a little about what you say, degree of freedom also. Little I'll discuss about its value in a CPCV, and then relation between CPCV and the universal gas constant. Everything we'll be discussing in the next lecture, along with the first law of thermodynamics and internal energy, heat exchange, and enthalpy, and all everything we'll be discussing in the next lecture. Uh, and then we will proceed to the fourth lecture. We'll proceed to the second law of thermodynamics. But please make up your mind that the next lecture will be a lengthy lecture. It may stretch to 1 hour, but I'll try to wind up it in 45 minutes. Okay. So this was our today's lecture, uh, in which we discussed about thermodynamic process and ideal gas equation. Ideal gas equation was based, so I just discussed, because with the help of that you can understand it. Okay, so thank you so much for joining me in this session. In next session, we'll discuss other topics of thermodynamics. Exiting 1, 2, 3.